The paper of the day is an array-based algorithm for simultaneous multidimensional aggregates. Computing multiple related groupies and aggregates is one of the core operations of online analytical processing, OLAP in short for applications. Recently, Gray et al. In 1995 proposed the cube operator, which computes groupie aggregation over all possible subsets of the specified dimensions. The rapid acceptance of the importance of this operator has led to a variant of the cube being proposed for the SQL standard. Several efficient algorithms for relational OLAP, ROLAP in short, have been developed to compute the cube. However, to our knowledge, there is nothing in the literature on how to compute the cube for multidimensional OLAP or MOLAP systems, which store their data in sparse arrays rather than in tables. In this paper, they present a MOLAP algorithm to compute the cube and compare it to a leading ROLAP algorithm. The comparison between the two is interesting, since although they are computing the same function, one is value-based, that is the ROLAP algorithm, whereas the other is position-based, that is the MOLAP algorithm. Paper tests shows that given appropriate compression techniques, the MOLAP algorithm is significantly faster than the ROLAP algorithm. In fact, the difference is so pronounced that this MOLAP algorithm may be useful for ROLAP systems as well as the MOLAP systems, since in many cases, instead of cubing a table directly, it is faster to first convert the table into an array, cube the array, and then convert the result back to the table. Continuing with the summary, this paper presents an algorithm for computing the cube operator over datasets that are stored as sparse arrays. In traditional relational databases, each cell is represented as a tuple with entries in the tuple denoting the attributes of the cell and one entry denoting the value. For example, the tuple shows Westtown 3 July 96 $34 presents a cell for shoes at the Westtown store on 3 July 96. The value of the cell sales is $34. When stored within a sparse array, the cell could be stored as the value 34, and the position within the sparse array could encode the remaining facts about the cell, that is product store date. The remainder of this chapter of this paper is devoted to an algorithm for computing the cube of data stored in such a sparse array. In prior work, three main ideas have been used to make ROLAP computation efficient, using some sort of grouping operation on the dimension attributes to bring together related tuples, that is sorting or hashing. Second, using the grouping performed on behalf of one of the sub-aggregates as a partial grouping to speed up the computation another sub-aggregate and to compute an aggregate over another aggregate rather than from the presumably much larger base table. Storing large arrays. One of the key problems in implementing an array-based cubing algorithm is efficiently managing the loading and storage of large arrays. The arrays can be too large to fit in main memory. The arrays may have a lot of empty values, that is, they are sparse in nature, and the data may need to be loaded from alternate data sources. Chunking. To handle loading arrays from which are too large for memory, the authors implement an existing chunking algorithm to divide the n-dimensional arrays into smaller n-dimensional chunks, storing each chunk on disk. Compression. Sparse arrays may contain significant blocks of empty values. Compression algorithm can run on these arrays to reduce the amount of memory necessary for storage and processing. The authors implement a chunked offset compression algorithm that stores a pair of values for each valid array entry consisting of the actual data for the cell and an offset describing the location of this value in the sparse array. Any empty values can be removed from the array. Ingesting data from relational tables. Loading data from table-based storage is done via partition-based algorithm that converts rows in a table to a location of chunked storage. After all data has been loaded into n-dimensional chunks, a second pass over the data compresses it. Performance. The authors provide performance results for the algorithm that shows that the array-based cubing algorithm is efficient for different size data sets, and it is widely more efficient than cubing a traditional relational database. The authors show that for some workloads, it is faster to load relational data into a sparse array structure to compute the cube than it is to compute the cube on the original relational data. Looking at the contributions of the paper, this paper presented the multi-array based method for cube computation. This method overlaps the computation of different groupies while using minimal memory for each groupie. They have proven that the dimension order used by the algorithm minimizes the total memory requirement for the algorithm. Performance results show that the multi-way array method performs much better than previously published ROLAP algorithms. In fact, they found that the performance benefits of the multi-way array method are so substantial that in their tests it was faster to load an array from a table, cube the array, dump the cubed array into tables than it was to cube the table directly. This suggests that this algorithm could be valuable in ROLAP as well as MOLAP systems. That is, it is not necessary that the system support arrays as a persistent storage type in order to obtain performance benefits from this algorithm.